Well, yes, the recording has just started. So welcome Fuensanta Aroca, who will speak on Newton's lemma for differential equations.
Okay, Daniela, can you take out the right?
Okay. Well, thanks a lot for inviting me. I will use the blackboard, and I made this thing bigger, and now I can make it smaller. Okay. So well, the title of my talk is Newton's lemma for differential equations. So I will start recalling Newton's algorithm to find solutions to find roots of equations with a series of polynomials that have the ring of series as coefficients. Let's start. Well, this is joint work with Giovanna Ilardi from the University of Naples. So what does Newton's lemma, we start with a polynomial or a series in two variables. It's the sum of ai, x to the I, y to the j, where aij are in characteristic zero, algebraically closed field. And we are looking for solutions as power series y of x such that f of x, y of x equals 0. We usually look for solutions around 0. So we ask f of 0, 0 to be equal to 0. And also the solution we look for, we want I of 0 equals 0. It depends, the existence of such solutions depends on where are we looking for them. For example, if we have I squared minus x cubed, the solution is going to be I of x equals x to the 3/2. So we need to look for solutions with rational exponents. They're going to be the form C0, this is I, x to the I over k, I from 0 to infinity. These are the solutions we are going to look for. These are called Puise series. They have rational exponents, but the denominator is bounded. The theorem of Newton-Puise states that these solutions always exist. How do we find the solutions? We start finding the first term. Instead of writing it like this, I will write it like this. So I x to the mu I with mu I less than mu I plus 1. And to find the solution, since it has infinitely many terms, it means to be able to find the first term, then the second term. So I will say that y of x equals c0 x to the mu 0 plus terms of higher order. And this is the part we want to find. And then we are going to iterate. Once we know which is the first term, it's very easy to find the second term, just doing the change of variables f of x equals to y plus c0 of x to the mu 0. And then the first term of this equation is going to be the second term of a solution to this other equation. That's Newton's method. How does it work? What does it say? The way to do Newton's method is we had f of xy equal to the sum of aij x to the I, y to the j. First, we define the support of f, which are the exponents that appear, ij, such that aij is different than 0. And then we draw the Newton polygon of f, which is the convex envelope of the support of f plus the first quadrant. We draw the support. To each point, we add the first order. And then we take the convex envelope. What does the Newton polygon method says? First, we need another definition, that is f restricted to an edge. F restricted to an edge is the sum of aij x to the I, y to the j, where ij are in the edge. So it means I have a series that may have infinite terms. And when I restrict it to an edge, I just stay with the points that are in the exponents that are in the edge. And we were looking for C0 x to the mu 0. So we need to know what is mu 0 and what is C0. Mu 0 turns out to be always minus 1 over the slope of L, where L is an edge of the Newton polygon. And C0 is a root of f restricted to the same edge, evaluated in one W. That's the Newton's method. I draw the Newton polygon, I find mu 0, C0, we substitute, and then again we can find the second term, the third term. Okay. How do we say the same thing? Well, actually, these two are the same as saying that C0 x to the mu 0 is a solution of f restricted to L. It is exactly the same. We start looking for a solution. We started looking for a solution of f, that is f of xy. And what we get is that C0, the first term, is going to be a solution of f restricted to some side. Okay. I'm going fast because I suppose I'm just reviewing. Now, how do we say this f restricted to L? in tropical language. Language. In tropical language, we have given f xy, and given a vector omega in R greater than 0 to 2. We define the omega order of f to be the minimum of omega times alpha, such that alpha is in the support of f. And the omega initial part of f to be the terms where the terms of order, the omega order, that is the sum of a ij x to the I, y to the j, where omega times ij is equal to the omega order of f. That is, if here is the support, and this is omega, we are doing the scalar product. It will be like we take the orthogonal to omega, start moving, and the first points I touch are going to be the initial part. Depending on how omega is, I have a different omega. If this were omega, now the omega initial part will be the term corresponding to this point. In this language, what is f restricted to L? If this is L, and suppose that I have here mu0, and this is L, such that mu0 is -1 over the slope of L. Then the vector 1 mu0 is orthogonal to the side. It's the same to say that mu0 is -1 over the slope of an edge than to say that 1 mu0 is orthogonal to the edge. This is equivalent. So if this is going to be the initial 1 mu0 part of f. That would be in tropical language. Okay. So saying that C0 x to the mu0 is a solution of f restricted to L is equivalent to saying that C0 x to the mu0 is a solution of the 1 mu0 initial part of f. Then Newton's theorem would say, Newton-Puiseux theorem in this language says that there exists a solution of f equals 0 of the form y equals c0 x to the mu 0 plus higher order terms if and only if c0 x to the mu 0 is a solution of the 1 mu 0 initial part of f. Okay. This Newton's, no? This would be Newton's lemma, and this is the key lemma to construct Newton's method. Now in tropical geometry, now the language of tropical geometry is easier if I want to pass to ideals. So for an ideal, the same. Now we have an ideal I in, now it would be k of x1, xn, y1, ym. And we are looking for y1 of x, that is going to be c1 x to the mu1 plus higher order terms. Ym is going to be cm x to the new m plus higher order terms. Now here, mu1 is a vector in Qn, because I am writing now x are vectors. When do I have a solution? So there exists a solution like this if and only if the m tuple of initial parts x to the mu n is a solution of, now what I'm going to have, the initial omega, comma, mu1, mu n, part of the ideal I. This is how we pass this to several variables. And this way you can construct, you can extend Newton's method. We are going to get a series with exponents in codes, but we can compute. This I did with Giovanna Ilardi and Lucia López de Mena. Now, we want to do the same, but for differential equations. Okay. Instead of working with f of xy, now we are going, now in the differential case, we are going to work with f of x, y, y prime, y to the order. Let's write L. This is the order of the equation. I should have one more. So it is the same. When do I have a solution? Instead of this, I have f of x, y, y prime. And the solution is going to be, I write f, x of y of x, y prime of x. All this has to be 0. So now our equation is of the form, the sum of ai j, x to the j, x to the I, y to the j0, y prime to the j1, times y to the jl.
Sorry, Fuensanta, I'm not sharing, but you have 4 minutes, you know, that you need to
Okay.
end in 4 minutes, and we don't know which is the problem you want to solve.
I want to extend Newton's method to differential equations. See? The same. Okay, so instead of having, now I just have more variables, which are y1. Instead of working with y prime, I am going to work with y prime is the derivative of y with respect to x. Instead of this, I am going to work with delta x, which is going to be x times y, just so that things are easier. So it's going to be like this. Y0, y1, yl. Where yi is delta x, y minus 1. The points we were associating to the first one were just to ai, yj. I was sending to ij. Now I am going to send this to I, the modulus of ij, where j is j0 plus jl. This is going to be the support. So the support of my new function is ij, such that a sub I j is different than 0. We can do exactly the same, the convex envelope, and we get exactly the same thing. Only instead of thinking or instead of taking edges, now we also have to take care of vertices, because there are some equations, for example, x plus xy prime, xy, no, y plus y prime, for example. The Newton polygon of, no, x plus y plus xy prime is just 1 point. And it does have a solution. So now instead of taking in account only edges, we have to take into account edges and vertices. Okay. But this is exactly the same, only we don't have this if and only if. We only have this one. This then. If something is the first term of a solution, just by assigning these points, we get exactly the same lemma. And also, in the case of several variables. Now, for several variables, we have to consider not only delta x, but we need to consider delta, the partial with respect to x1, partial with respect to xn. And this is going to be delta x1, delta xn is going to be x1, delta xn, xn.
Is it a good time to stop?
And we get the same lemma. Yes.
Thank you.
We can stop here.
Thank you. So we have time for one quick question.
So I have one stupid question. You said that there is a slope, but can you predict which L at the beginning? That there is one of the edges. Can you predict which one?
No, for each edge, you're going to get as many solutions as the height of the edge.
Of the length
Always. This is in the algebraic case. Now,
Yeah.
when you pass to differential case, sometimes there are no solutions. If you're looking in Puise, so sometimes you don't have solutions. Sometimes a vertex gives, when you have also vertices, gives you solutions, and it gives infinitely many solutions. So this is you still have Newton's lemma, but just in one side. See, in Newton's lemma, in the algebraic case, for each edge and for each root of the polygon associated to the edge,
Yeah.
you know that there is a solution. When you pass to the differential case, no. In the case of ordinary equations of degree 1, there always exists a solution, but not for every edge. There is a way to choose an edge. So, but anyhow, this gives you a fund, like all that will give you all possible first terms of solutions. See, in the case of when you are in the algebraic case, you have a fund, and exactly the fund is when there is no when the initial equation doesn't have a monomial, then I do have a solution and I know I can continue. But in the differential case, no. You know, if there is a solution, it will start with the solution of the initial equation. But anyhow, you get a fund, so it's still a structure. And what you get extra is you don't have to look just for ideals, but you have differential ideals, which makes the ideal kind of nicer, maybe. You're not anymore in the Noetherian case. There are many things that change. But for example, this is very useful to find equations that don't have solution, because you've seen all the initial equations don't have a solution, so this doesn't have a solution.
Thank you again for your presentation.